All right, welcome everyone at my session. Today I want to talk about native versus cross-platform development without double cost. Let me first quickly introduce myself. I'm the founder and CEO of Egenic. We're an app agency who have been working on apps since 2010. So I have 12 years of native app development experience. As a founder, I get to manage the company, but I'm also very technical. In our projects, I typically have the role of solution architect. And we do a lot of media apps, and I'm also the solution architect of the Dutch COVID apps, like the vaccination passport, etc. And finally, I'm the organizer of the App DevCon conference. So I tend to organize conferences myself. So when we talk about native versus cross-platform development, I don't want this to be a native versus cross-platform discussion. I want to look at optimizing native development. But to do that, we first have to look at the benefits of native app development and the drawbacks, and compare those to the benefits and drawbacks that you get when you do cross-platform development. So when we look at the benefits, the native benefits are typically that native development is how the platform vendors, Android, Apple, Google and Apple, how they actually intended it. And it's very easy to use direct integration of the device features. And native development, you build apps that are really, really closely to the platforms. So the UIs are typically very similar to what the users expect on those platforms. Other benefits include things like best performance. There are no abstractions to deal with. You have smaller binaries, and there's a really huge, large ecosystem because most of the apps these days are still developed natively. But of course, cross-platform has its benefits as well. And in this talk, I want to look at if we can bring over some of those benefits to native development. Of course, the obvious benefit of cross-platform development is that you have one code base to rule them all, only one code base to deal with. Also, it's useful that you have common abstraction of device features. There's only one interface you have to deal with, and it works on both Android and iOS. And the benefit is that you have the same UI, one UI on all platforms. Unless you spend some additional time, then you can make differences. But the same UI, that's kind of a benefit. Also, cross-platform development these days is no longer limited to iOS and Android. For example, if you're using Flutter, you can also use it on the web. If you look at the drawbacks, the interesting thing is that the same UI on all platforms, which I just touted as a benefit of cross-platform development, is actually also a little bit of a drawback. Because for experienced users, that same UI might feel off. Users are not don't want an app that works the same on Android as on iOS. They want an app that works the same on iOS as all the other apps that they're used to on iOS. It's also kind of a bit of a drawback. Native drawback, of course, is that you have two code bases to maintain. And you need to do separate testing for Android and iOS. But that's kind of a drawback on both sides, because even if you use cross-platform tooling, you're still going to have to test that on both iOS and Android to make sure your app works everywhere. So what if we could harness the benefits of native development? Because we want all of those native advantages, but still gaining some of these benefits that cross-platform offers. And most notably, the promise that it reduces development time. Can we look into native development and see if we can reduce development time somehow? What we want to avoid is that when we do native development, that we're working in islands. Like this is like the basic setup that we want to avoid. You have an iOS team that works on an app. You have an Android team that works on an app. 1 + 1 is 2, so you effectively double the cost of development. That's something we would like to avoid, because that's like a waste of everyone's time, and that's not really nice. That would be a huge drawback of native development. But in this talk, I'm going to show a number of ways to deal with that. Well, the first thing I want to talk about is shared architecture. Years ago, when the Android and iOS platforms just came about, they were wildly different. There were two completely different ecosystems. Objective-C on the iOS side and Java on the Android side, two completely different languages. There was not much in common between them. So there were two usually different ecosystems. So when working on an app, you typically had these island mentalities. You had an Android team working on something, you had an iOS team working on something, and they didn't have much in common. But these days, these paradigms are converging. These days, we work in Swift on the iOS platform. We work in Kotlin on the Android platform. And Swift and Kotlin are very, very much more akin than Objective-C and Java ever were. So it's much closer. They have the same paradigms. They have a lot of the same principles behind them. So it's more like they're now brother and sister languages instead of distant cousins. On the iOS side, you have Swift UI for building nice UIs. On the Android side, you have Compose, and even those have very comparable properties. Now, and there's even in the terms of asynchronous development, you have all kinds of technical terms that are very similar. And one of the most common things is that in both platforms these days, it's common to work with the MVVM paradigm. And I'll get to that in the next slide. So what does the shared architecture approach means? Shared architecture basically means that we optimize the commonalities between the platforms. And in the shared architecture approach, an iOS and an Android engineer together creates the technical design for both apps. So the data model could be the same on Android and iOS. There's only one definition of how the business logic should work. There's only one approach to working with the backend. So all of these things are items that are not very iOS or Android specific. And in the shared architecture approach, together, you basically set the stage for the development on top of this architecture. Conceptually, this means thinking about the data model. And in an MVVM design paradigm, it means thinking about the model layer together, because both platforms can then share the same models. You have to think about the view model layer, which is very similar, and you have the view layer. But if you look at how that then translates to the platforms, you'll see that on the iOS and Android side, the UIs will be the things that are the most different, because you want to optimize the experience for Android user paradigms or iOS user paradigms. The view models are already a little bit more closer, because under the hood, they use repositories and models or data classes in Android that are very similar, because you've together defined the model layer, and these should be comparable across the two platforms. And even your data model, under the hood, both Android and iOS can use a SQLite data model, where iOS uses core data as an abstraction layer. In Android, Room is a common abstraction layer. But in both cases, they can use the same data model. So these are very close together and can be developed together as a shared architecture, where you're still writing your own code on both platforms then. If you look at the impact on the project, if you remember the previous 1 + 1 = 2 slide, then it's now slightly different. What if we can spend 30% of our time together on the same things? And that's basically the shared architecture that we make in the beginning, but it's also during the project, the discussions and the decisions we make that are architectural based. What if we can move that to the shared layer so that iOS and Android can do that together, and the development is only 70% of that? Then the end result is that 0.7 plus 0.3 plus 0.7 is 1.7, and it's no longer a factor 2. This is a completely unscientific method, so it's kind of like a model for how things could be optimized, so it won't be literally 1.7 times the development cost, but you get the idea that by moving stuff to a shared layer, even if it's just the architecture and how the app works, can already save quite some time. The second item that I would like to discuss is what I call asynchronous development. Asynchronous development basically means that the two development teams are out of sync and are not working on the same things at the same time. I want to illustrate that with an example. Suppose the iOS team works on feature A. Instead of both teams working on feature A, the Android team starts off with feature B. And the interesting thing is that when you do development, a lot of the things that you do aren't specifically writing code. It's also a lot of time that goes into like how should this feature work? What APIs do I need to call? What things do I need to do to make this feature work? So a lot of the things, a lot of the time that you spend on developing a feature is not actually writing the code. It's actually thinking about how that code should be written. Now, if you do this asynchronous development, then both teams can think about different things. If they think about different things and figure out all these different things and then write the code, you have two features that are more or less completely developed, and then you turn things around. Basically, because of the similarities between the platforms, because of the commonalities between Swift on the one hand and Kotlin on the other hand, you can basically have, you can easily port the code instead of develop the code. So instead of developing feature B for iOS now, you basically port feature B that the Android team already has written. You can look at their code, you can look at their documentation, you can look at their app, and you can basically see what it needs to be like and port that over to your platform. And porting things is a lot easier than developing things, because you've taken out all of those investigative time sinks where you need to investigate how something needs to work. So when we do that specifically for all the features, so we basically take turns in developing these features. What we then get, if we put that in a whole project perspective, is that we can reduce the development time even more. Let's say that porting a feature takes about half the time of developing the feature, and putting that in the entire timeline, then you get to numbers where you say, okay, now we've already moved 20% of our time to the shared architecture, but we've also reduced the actual time it takes to develop the app by 0.35. So in this case, we get to a total of just 1.5. So we have 2 native apps, but it has taken us only 1.5 times the time it would have taken to only develop one of these native apps. So that already makes it quite efficient. But I'd like to discuss a third way. And the third way is what I call the shared core method. With a shared core, basically that means that you develop your apps natively, especially the UI is developed natively in Swift or Kotlin. But there's a shared core that's developed in some common shared language. So that means that although you have 2 native applications, there is a piece inside that application that only has one code base. And typically you can do that for the repositories, the data classes, and the storage. So basically like kind of the model and the business logic side of the applications. But it's kind of flexible. Depending on which core you use and depending on the nature of your application, you might even be able to reuse some of the view model logic inside your shared core. Sometimes you want to have some of the device features in the shared core, but if they're very specific, that will be developed natively. So where the shared core lives and how big it is in comparison to the rest of the application kind of depends on the nature of the application. But you can imagine that if you have a part of the application that you have to write only once, you're getting close to the benefits of doing cross-platform development, because the time you're spending on the different platforms is basically the time that you'll want to spend on the different platforms to make them iOS or Android native. So the shared code could be written in a number of languages. Basically, any language that allows you to compile it with a certain compiler and into a certain module that can be implemented in the application platforms, then you're able to use that language. Some common languages that you could use is Kotlin multi-platform, which I'll get to in a minute. You could use C or C++, which is always reusable in a large number of applications, or popular languages like Go or Rust. If you look at Kotlin multi-platform for that shared core, the interesting thing is that you don't need to add a third stack. Like if you're introducing a third language to make that common core, there's a third language that you need to learn. Similar to how if you're using a cross-platform tool, you need to learn both the native platforms and that cross-platform tool. So it's kind of a disadvantage that you have a third stack. However, with Kotlin multi-platform, the language is the same as you're using on the native Android side. So basically, you only have 2 stacks to learn. You build the native iOS app in Swift, you build the native Android app in Kotlin, and that shared core that's used across both is also written in Kotlin. So that's very useful, because that means that the development could be handled by the same Android devs that do the native Android applications. What I find interesting about Kotlin multi-platform is that it is specifically created for this shared core use case. Here's a screenshot of the website of Kotlin multi-platform. And it's actually basically how they intend to use it. They basically say they write this core in Kotlin multi-platform, and then wrap a native Android or a native iOS app around it. That's quite interesting. If you use any of the other languages, each language has its benefits or drawbacks. I don't want to go into them in much detail, but if you are going to do a shared core, basically select the language that fits your use case. Like if you're doing a lot of cryptography things, find a language that's strong in the cryptography side. If you need to do a lot of low-level device interfacing, C and C++ might be more useful. So basically, make sure you select a language that fits the use case. But in any case, do keep into account that shared core in another language is an extra stack that you need to to manage. If you look at the shared core benefits and you put that in that hypothetical model of cost analysis, it depends on, like I said, it depends on where you position that core inside your application. But suppose that you are able to move 60% of the code of your application into that shared core. And for example, 60% is business logic, data models, etc., and all of the things that can be shared. Whereas 40% is spent on the UI and making things pretty and making things work for the user. Then you could end up at a model like this, where 40% is spent on both platforms on the user interface and 60% is spent on the shared core. So the total cost factor of remaining native with two platforms to support would be 1.4, compared to the one of just having one platform. Now, of course, you can combine all the things. Like I've mentioned 3 ways to optimize native development. What if you employed all 3 of them? Well, that makes like a really nice picture with a lot of arrows, and a hypothetical score of only 1.2, because the benefits you have of all these methods to combine together and calculate it would mean that you're only spending 0.3, like 30% of one platform time on the actual platform-specific features, and 60% of the time on the shared core, and then 30 on the other platform. So the total effort that you're now spending on 2 applications on 2 platforms is only 1.2 times the amount of time you would spend on having to develop only a single platform. Well, obviously, that's why I put a question mark on it. That's kind of an ideal situation, because 1.2, that's a bit ambitious. But also because the methods aren't fully complementary. It's not like you can put all of them in a chain, but they overlap slightly. Like shared core and shared architecture have some aspects that are similar. And if you already do the shared core stuff and you've pushed all of the native code mostly to the user interface, then the porting effect, like that asynchronous development where you take turns in developing a feature, becomes a bit damped, because that will only be user interface codes, which is likely to be different on both platforms anyway. But in our experience in the past 12 years, we've started out with just the island approach, and now we're using a mix of these 3 methods. In our experience, a factor of 1.3 to 1.6 is definitely achievable. So we never spend double the time on if we need to support 2 platforms. We've become quite efficient at it. Of course, there are some other considerations to take into account. You also have to consider, like if you're doing cost comparison, like how much does it cost to do native development? You need to consider the size of the project, of course. Like if you have a 4-person project and you need to have separate iOS and Android developers in there, then there's a good use case to do cross-platform technology, because without all of the benefits I just mentioned here, the additional cost of adding developers is already quite, you're already almost doubling the team just by adding the developers, regardless of how efficient they are. On a 60-person project, on the other hand, I've worked in some very large projects where the development team is actually a very small portion of the total group. In a 60-person project with business analysts, architects, testers, a whole shebang of people, then adding 2 developers, for example, to add another native platforms, it's not a big deal. I mean, even if they're not efficient and even if they're not using any of these optimizations and just you have 2 islands doing that work, adding those developers, is only a cost factor of about 3% increase. So, of course, you have to take into account the nature of your project to do this. Other considerations that you have to make is that you have existing skills in the team. You could say, hey, I want to do native development, but if you don't have any iOS and Android developers, then it's quite difficult to do that. And therefore, you see a lot of teams that come from web development and that want to also do app development. They'll use something like React Native, because then you write an app in web technology. So it's not just about cost. You also have to look into the skills that you have in-house. And finally, the nature of the project, of course, like a throwaway marketing UI only project, you can benefit much more in a cross-platform environment, because you can easily make something quick that you're going to toss out anyway. But if it's a strategic app that you will need to support for years to come, and you don't want to rely on technology that might not be there in a couple of years, then you benefit more from native development. Finally, before we go to some of the questions, we've been doing this for quite a number of years. So over this past 12 years, we've become quite efficient at native app development without doubling the costs for our customers. But we're continuously doing research. So I expect that in the future, we will even make more, become more effective in native development. For example, this is just an example of a screenshot of one of the researchers at our company that's currently working on researching tools such as Kotlin multi-platform. And they're doing lots of experiments and lots of experiments and research into how to make the development more efficiently. One of the things that, like I said, the view models, like the layer between the UI and the data models, that's often quite different between the platforms. Currently, we're looking into how we can even do that in a shared core, such as Kotlin multi-platform. So I expect that in the future, we'll become even more efficient at this native development, remaining native in the user interface, very efficient on the development side. And then we'll continue to share our findings learning at conferences like this or at DEFCON, our own conference. But that's what I wanted to share. And then I'll switch to the tab where I can see if there are any questions. What about the feature parity when doing async development? Kubilai is asking that question. What about the feature parity when doing async development? Do you wait until both platforms implement both features and then release? Yeah, that kind of depends. Like if those are features that are easily, like if you want to release something that's not quite yet the finished product, then you have to carefully look into how you develop these features. But if the iterations are small, like the features are broken down into smaller parts that you can easily swap around, and then waiting for a release until both platforms have both features is, of course, a good choice, because then you're sure that the users will see the same platforms. And actually, what we find is that typically it's easier to actually release with the same features, because if they're not reinventing the wheel, but actually looking at the other feature on the other platform and porting that, yeah, the chance that those apps are similar in feature set is much larger. Let me see. Sebastian asks, can you recommend a library that would generate version data models controlled by a backend that native languages could pull? I know that within our company, we use a number of those libraries. I would have to check with our engineers which ones they are using and which ones they are happy with. But I do know that, yeah, you can definitely, if, for example, your API specification of your backend is written in, let's say, open API specifications, there are definitely generators that can generate native code based on that language. So that's another option that could be considered. But I'll publish the slides later anyway, so I'll check if we have some recommendations on those libraries, and maybe I'll add a slide with those. Let me check. This was the question. What are your thoughts on blocking dependency on the shared code when the same feature needs to be developed and delivered at the same time on both platforms? That's a good question, and that's a matter of project planning. And even without shared code bases, there are often dependencies that you need to take into account. So that's definitely a challenge that you need to take up with a project manager. You need to have a planning where you have a critical path where that shared element is on the critical path for both applications. So it's typically you'll want to work on that shared part first so that both platforms can actually start working on it. One of the ways we solve that dependency is that while the shared core is being built, you could mock it. So, for example, you have an interface that gives dummy data while somebody works on a shared component that actually talks to a backend API. So there are some ways to actually cope with those dependencies. But like any dependency, it's something you'll need to take into account in the project planning. Do you think Kotlin multi-platform is production ready? That's a good question, because that's a matter of opinion. We are actually using it in several production apps. I think we have about 20 apps in production right now that are using Kotlin multi-platform in one way or another. Some of them only as a really small component that does some backend interaction, and some that use a little bit more. So yes, we definitely use it in production, and with success. And obviously, like with any new stack, there will be some things to take into account. But that's like basically the case with any library or external tool that you use, that you have to take into account. What's your recommendation of tech stack for the common code base for iOS and Android? Yeah, my preference at the moment is Kotlin multi-platform because of the benefits I mentioned, because you don't have to have an additional stack and an additional skill set to develop that shared core. So Kotlin multi-platform is definitely currently my language of choice for that stack. I think I can do one more because we're reaching the end of the session. What's the performance impact in accessing it from native iOS code? In our experience, the performance impact of using Kotlin native, I keep saying Kotlin native because that's the old name before they renamed it to Kotlin multi-platform. But the performance impact of Kotlin multi-platform is quite small because basically it's compiled to code that runs natively on the platform. So at runtime, you don't have a lot of drawbacks from it. Kind of depends like on how much code you put in there and obviously how you've architectured that component. But from Kotlin multi-platform itself, the biggest downside in the time it takes is that you need to compile something, you need to embed that in your iOS application. So that takes some time during development, but at runtime, we haven't noticed any significant performance loss. This was the end of the session, so I'll look at the session. There are a lot more questions. I'll answer those in the chat. Hopefully the chat remains open so that you can see the answers. But as for the audio and video, I'll have to end the session now, and I thank you all for your attention.